Hello everyone. The title of this video is Determine whether a relation represents a function. Okay, now each example I'm going to be doing in this video is taken directly from a free online textbook at openstax.org. I'm in their Algebra and Trigonometry text, section 3.1, titled Functions and Function Notation. And I'm working under the heading Determining whether a relation represents a function. Now each example will either be an example from the reading or one of the try it problems from the reading or an exercise from the end of the section that's related to this particular objective. Okay, so I'll be coming back to this reading here because I have all the examples written out on paper, and some of these, like I said, are going to be either just examples from the reading or try it problems from the reading. So example one, I said, I'm going to do try it number one from the reading. But first I want to talk a little bit about some definitions. All right. So first off, a relation. Now a relation, in the reading, they simply say it's a set of ordered pairs. A set of ordered pairs. Another way you can think of a relation, it's just a bunch of, again, pairings of elements from one set. Right? So say there's here's set A with several elements in it. Right? Two elements of another set. Right? So there's pictures here. There's set B, and here's some elements, in this set as well. These little dots represent elements. And all a relation is pairings, right? It's taking elements from one set and pairing them with elements of another. So maybe I compare this element here with this element here and this element here. And I compare this element with this element. And I can take this element from set A and pair it with this element from set B, and so on. Right? It's just pairings. That's all a relation is. And instead of drawing big pictures like this, say this element from set A was called X, this dot here, and this element in set B was called, Y, and this element was called Z. Pairings are represented by, ordered pairs, like when you were graphing on the XY coordinate plane, those kinds of ordered pairs. So these arrows I'm drawing in this picture can be represented by an ordered pair. X is paired with Y, so X comma Y, is in this relation that I'm drawing. Also, X comma Z, X comma Z is also in the relation, right? And so on, right? If I draw I can draw pictures with arrows. This is called a mapping or an arrow diagram. You can write a relation as a set with braces, just as a set of ordered pairs. You can make graphs. There's lots of ways to picture relations. All right, and these first coordinates of the ordered pairs are these x coordinates here. The first coordinates are sometimes referred to as inputs. Right, inputs. And the second coordinates right? Like the y and the z here in the ordered pair. What those first coordinates are paired with. Right? The second coordinates in these ordered pairs are often referred to as, the outputs. Right? Right, and then each relation has, these, again, two sets where elements of one set are being paired with elements of another. The set of all inputs, right? So just some more definitions here. Sorry, there's a lot of definitions to start this. The set of all inputs is called the domain. Right? The set of all inputs is called the domain of the relation, or the set of all the first coordinates, right? This set A here would be called the domain. And the set of all outputs Alright, the set of all outputs, the second coordinates in these ordered pairs, or this set B where the arrows are pointing at, this is called the range of the relation. Alright, and then one final definition. They're asking us to determine whether a given relation, some mapping, some pairing between two sets, we're asked to determine if a relation is a function. Right? So we have one more definition here. A function. Right? A function is a relation Alright, so it's a set of ordered pairs still. Alright, it is a relationship, a pairing from one set of elements to another set of elements. Alright, but it's special. There's something special about a function. It's a relation in which each input or each value of the domain, or each element, value or element of the domain, is paired with exactly one. Or corresponds to, is paired with, corresponds to, but is paired with exactly one. No more than one. Exactly one value of the range. So I'm going to put this in a box. Right? This is very, very important. Right? This is what we're basing our entire rest of the video on here. Right? The definition of a function. Right? So if you look back at my picture up here, where I had, set A was the domain and set B was the range. Right? I had the range elements, inputs, outputs, and there were these pairings. Right? You see that this would not be a function. It would not, because there's this element from the domain that maps to more than one element of the range. Right? Not exactly one. It's got to be exactly one, not more than one. Right? So that picture there is an example of not a function. Right? A relation that's not a function. All right, so all functions are relations, sets of ordered pairs, but not all relations are functions. Please understand this. Okay. And then one other thing about functions, finally, one other thing about these functions, before I get on to our first example, and I'll eventually get there, is just some wording, right? Some language. You may see, quantity. They'll say some quantity A, is a function of. You'll see these words, is a function of B. Now, what does this mean? What does this mean when people say blah is a function of blah? All right. All right. Well, this means, like from the definition of a function, when I say A is a function of B, that means that each value of B is paired with exactly one value of A. Right, so kind of the same thing, but it's just a way of saying it. Right? Just wording. So each value of the second quantity, right, each value of B is paired with, again, exactly one. I'll say it one more time here, right? Exactly one value of A. All right, so if you had, here's set B, here's set A. That means, take all the elements of B, they're paired with exactly one element of A, right? So if I did these pairings again, this element pairs with this element, and this element pairs with this element, and this element, say, pairs with this element, right? But every element of the second quantity pairs with exactly one element of that first quantity, right? So the input set, the domain is the B here, and the range set, right, or A is here, the set of outputs. Okay, so yeah, so we're going to see this wording come up as well. A is a function of B, some quantity. One quantity is a function of another quantity. All right, so like in try it problem number 1, right? So that's, like I said, my first example here is try it number 1. So back in the reading, again, I'm expecting that you read through this, right? Look at the examples as well. All right, so here's try it number 1, right? So it says table 2, right? Table 2 lists the 5 greatest baseball players of all time in order of rank. Now, of course, this is, subjective. According to some people, they even put the source somewhere, and then they put number 1. Doesn't matter, right? So here I have 2 sets, right? I have 2 sets, and every single relation and function, right, will have 2 sets involved. A set of, players. Got 5 players here: Babe Ruth, Willie Mays, Ty Cobb, Walter Johnson, Hank Aaron. And a set of numbers, a set of these ranks, just the numbers 1, 2, 3, 4, and 5. All right, and then look at part A. Right. Is the rank a function of the player name? All right, so remember how I said A is a function of B. Right. All right, so I'm going to come back here and I'll have this written out. All right. So they asked this question, right? Is rank a function of player name? So this means that for every player name needs to be paired with, exactly one rank. Right? Does this happen? Right? So I'm going to make a little mapping, right? Now again, you can represent a relation in many different ways, right? Here's a mapping, a little arrow diagram. So you got the player names over in one set, right? Again, I'm just making a big wavy box here. Here are the player names, right? The set of player names. And you had, you know, Babe Ruth. Make a little dot representing Babe Ruth and Willie Mays. Another dot, you know, for that element, that player name. Ty Cobb. Walter Johnson. And Hank Aaron. Alright, so there's the set of player names, and these will be the inputs when they're asking this question. In the second question, you'll notice they switch these, so inputs and outputs change. They switch, but then over on this side, we'll have another set, the ranks, the set of ranks, which are just numbers, right? 1, 2, 3, 4, and 5. Right. Now, you can tell from the table what the pairings are. You know, Babe Ruth is paired with the number 1. Right? They're right across from each other. Willie Mays is paired with 2, Ty Cobb with 3, Walter Johnson with 4, and Hank Aaron with 5. So, I mean, you can see it from the table. I mean, I'll make this little drawing here, but Babe Ruth is paired with, you know, the number 1. Willie Mays is paired with the number 2, and that's it, right? Ty Cobb is ranked 3. Walter Johnson ranked 4. Hank Aaron ranked 5, right? And that's it. You know, notice that every player name is paired with exactly 1 rank. Every player name is paired with exactly 1 rank. So yes, rank is a function of player name. Since every player name is paired with exactly 1 rank. All right, so I hope that's clear. All right. Now, part B, right? Part B of triad number 1 asks the other way around. Is the player name set a function of the rank? Right, so now the domain and range are switching here. All right, so I'll write this out again. Okay, so again, part B is player name a function of rank. So this time rank is going to be the input values and player name the output values. Right? The domain will be the set of the ranks. The range will be the set of the player names. And again, if player name is a function of rank, that means that each rank will be paired with exactly 1 player name. All right, now I know it's silly. You can probably already tell from the table or from the last picture, but draw another mapping here. There's only 5 of these. It's not so bad. So now the ranks are the domain values, right? We have 1, 2, 3, 4, and 5 were the ranks. And then over here, right, the outputs, where the range is, are the player names. Now I'm just going to put their initials this time, just to save on writing. But you had, you know, Babe Ruth, right, BR, the Willie Mays, right, WM. You had Ty Cobb, TC, right. You had Walter Johnson, WJ, and you had Hank Aaron, HA. Okay, just so I don't have to write all the names again. And again, it's probably incredibly clear from the table that, you know, the rank of 1 is paired with Babe Ruth. Right? They're in that row together. The rank of 2 is paired with Willie Mays. The rank of 3 is paired with Ty Cobb, and so on. Right? So, yeah, so a very similar picture, but just going the other way around, right? And they would actually call what I'm doing here the inverse relation, but you'll talk about inverses in future videos, future sections. Right? And then the rank of 2 pairs to, Willie Mays. The rank of 3 pairs with Ty Cobb. The rank of 4 pairs with Walter Johnson. And the rank of 5th, 5 pairs with Hank Aaron. And notice again, there's only one arrow, coming off of all these ranks. Each rank is paired with exactly one player name. So because each rank is paired with exactly one player name, then the answer is yes again. Yes, rank is a function of player name. Oh, sorry, the other way around. I apologize. I was thinking of part A again. Right? Yeah, it's because every rank pairs with exactly one player name. You would say that player name is a function of rank. My apologies, I messed that up. Yes, player name is a function of rank. All right, one more time. When they say it this way, something is a function of something else. That second quantity is the domain. The first quantity is the range. Right? Great. Wonderful. Now, that's example 1. All right, that was try it number 1. Example 2 I've got for you. I'm gonna try to do. I'm gonna do try it number 3. All right, let's see what that looks like. So going back to the reading here again. Function notation. Blah blah blah. All right. Try it 3 is more tables, some table stuff. Example 5. There's try it number 3. And all it's simply asking is, does table 9 here represent a function where they're telling us what's the inputs and what's the outputs, right? The previous table with the player names and the ranks, we could switch it up. Player names could be the inputs and ranks could be the outputs, and we switched it up and had the ranks be the inputs and the player names be the outputs. Here they're telling us, these are the inputs, 1, 2, 3. And these are their corresponding outputs, 10, 100, 1,000. So you can draw little arrows if you want, but the domain is, the set 1, 2, 3. The range is the set 10, 100, 1,000. And clearly, every value in the domain pairs with exactly one value in the range. Every input pairs with exactly one output. 1 pairs with 10 and nothing else. 2 pairs with 100 and nothing else. 3 pairs with 1,000 and nothing else. So yes, right, I'm very simply going to write yes. Right. Table 9 is a function. Right. Yes, table 9 represents a function. It satisfies the definition. Now, so far, right, everything we've seen so far has been a function, right? Every value of the domain corresponds to or maps to or pairs with exactly one value of the range. But that is not always the case. I mean, look at my first picture here, right? This wouldn't be a function if set A was the domain and set B was the range, right? Just look at which direction the arrows are going. Because of this value, right? This value here, x, pairs with more than one value, right? So not a function. We're going to see more stuff like that also, right? Not everything's a function. All right. So now we're just asked the question, are these functions, right? So is the relation, right? Is the given relation a function? is the question being asked now. Right? Is the relation given a function? Now we're actually given sets of ordered pairs instead of tables. Right? So, here's an ordered pair. Input A pairs with output B. And here's another ordered pair. Input C pairs with output D. And one other ordered pair, input A, output C. All right, so I'm going to do some, so the domain here, right, the domain is just the set of the inputs, which are A and C. Right, it's all the first coordinates. And there's no need to write repeats, right? You see how there's two values of A in the first coordinate. There's no need to write repeats. The range, right, the set of outputs, are all the second coordinates. And again, don't write repeats if you don't need to, right? Don't write repeats. B, D, and C, right? B, D, and C is in the range. And I can draw a mapping if I want, right? One of those arrow diagrams. Now you can probably already tell me that this is not a function. All right, I get it. All right. You see A from the domain maps to B, but also to C. Right? This element of A, this input of A, pairs with more than one output, more than one element of the range. That in a function, it's got to pair with exactly one. But yeah, so I could put the domain in a little box, right? The elements just A and C, right? A gets a dot, C gets a dot, right? And then over here on the other side, the range, right? Just a little box or whatever. And then here's element B, right? Element D, element C, and then drawing my little arrows, right? We see A pairs with B, right? The ordered pair A, B. So A pairs with B, I draw an arrow. C pairs with D. Right? C from the domain pairs with D from the range. And A pairs with C. So A back to A again. There's another arrow coming to C. But you see there are, element A is pairs with, more than one element of the range. Not exactly one, right? And as soon as you find one element of the domain that does this, it's not a function, right? In a function, every element of the domain has to pair with exactly one element of the range. So this relation, right? This relation is not a function. Right? Simple, simple. I feel. Okay. So I'm doing the same thing for example 4 here. Right, question 4. Again, we're given another set of ordered pairs, just 3 ordered pairs, right? Now, a relation can have 3 ordered pairs, 4 ordered pairs, 1 ordered pair, infinitely many ordered pairs, right? We'll see plenty of relations in the future with infinitely many ordered pairs. We're still asking the same questions. Is this relation a function, right? Is every input paired with exactly one output? So here we have -1 is paired with -1, -2 is paired with -2, -3 is paired with. This is a function, right? So again, I'll state the domain. And again, there aren't any repeats, right? It's just all the first coordinates, -1, -2, and -3. And I'll state the range, right, which is all the second coordinates, right? So the set with -1, -2, and -3 in it again. And I mean, you could, if you spread them out a little bit, you could make a little arrow diagram here. You know, -1 pairs with -1. Right? -1 from the domain pairs with -1 from the range. So I'm just kind of doing a mapping with the sets themselves. -2 pairs with -2. -3 pairs with -3. And you see that every single value of the domain has exactly one arrow coming off of it to a value of the range. Every value of the domain pairs with exactly one value of the range. So this relation is a function. It satisfies the definition. This relation is a function. Wonderful. Okay. Moving on. Got next one's very similar. Another set of ordered pairs. Right, and then after this, we're going to get into equations that represent, relations with infinitely many ordered pairs. All right, so once again here, just a finite number of ordered pairs, just 4 of them. The domain, right, is just 2, 7, 15, and 7 again. Don't write 7 twice, right? Just 2, 7, and 15, all the first coordinates. Right? And the range is the set of the second coordinates, the outputs 5, 11, 8, and 9. Right? 5, 8, 9, and 11. Usually they're put in lowest to highest order. It doesn't matter as long as you list out the elements that are the outputs. And then I'll just do a little arrow mapping here, a little arrow diagram. 2 from the domain pairs with 5 from the range, right? 2 to 5, little arrow there. 7 to 11, right? 7 to 11. 15 to 8. And 7 to 9. So I'm back at 7, and I've got, right, a second arrow coming off of 7 here, right? That's a problem, right? 2 arrows coming off of 7 from the domain. So there's a value of the domain that doesn't correspond with exactly one value of the range. It corresponds with more than one value of the range, right? So once again, this relation is not a function. Okay. Easy enough. Now, when you have pairs of numbers, like number 5 is here, and I guess I could have done this with number 4 as well, right? Because there were also pairs of numbers. But when your ordered pairs are pairs of numbers, you can also make a graph on the xy plane. Right, you have the horizontal x-axis, which will be the input values. The values represent possible values of the domain. And then you have the vertical, y-axis, which will represent possible outputs, right, possible values of the range. And if I were to plot these points, 2 for the input, 5 for the output, right, there's one ordered pair in this relation. There's 2, 5, right? And then 7 for the input, 11 for the output. Let's just say that's up here. I didn't do this very well, sorry. But 7 for the input, 11, that'd be above 5, right? 11 for the output, there's 7, 11. Then 15 for the input, right? Again, let's just, too many notches here. Let's just say 15 would be to the right of 7 on that number line. And 8, which would be above 5. I know this is terrible, but there's 8, right? So 15 for the input, 8 for the output, right? And then finally 7, 9, right? Should be a little bit above 8. Let's just say 9's here. on the y-axis. 7 input, 9 output. There's a graph, a very, very, very bad graph, but a graph nonetheless. And then we'll see this in a future video, but we'll talk. You can look at a graph of a relation and see if it's a function or not by performing something called the vertical line test. Now I'm just going to bring it up now. I'm not going to say really I'll say out loud what it is. I just won't write it. Now, if you draw any vertical line, this vertical line, this vertical line, this vertical line, it's going to hit the graph at most one time, right? If it's a function. If it's a function, it'll hit it at most one time. Here it doesn't hit the graph at all, doesn't hit the graph at all, doesn't hit the graph at all. This vertical line here, hits the graph once. This vertical line doesn't hit the graph. This vertical line, however, at 7, hits the graph twice. And so I can say, hey, is not a function. Right? That leads me to the fact that this is not a function because there's a vertical line that hits the graph more than once somewhere. All right, if that ever happens, if a vertical line ever hits the graph more than once, then they would say that y is not a function of x. Right? Okay, but again, that's neither here nor there, but just know that this will come up in a future video in more detail. All right. Now we're going to get into equations. Right? Equations with two variables, and they'll be just x and y here. All right, so they're asking us to determine whether the relation represents y as a function of x. Remember what that means. When I say y as a function of x, or is y a function of x, that means for each value of x, or each value of x is paired with or corresponds to exactly one value or no values, because some of these certain values of x might not pair with a value of y at all. So exactly one, or I should say at most one, because like I said, there are some values you can plug in that don't correspond to a y value at all, right? Like that vertical line test where the vertical lines weren't hitting the graph. So each value of x is paired with at most one, exactly one value of y. Right, same as I was writing earlier. Right. All right. So what we're going to do here is we're going to solve each of these for y. Right. You solve for y. Right. Get y equals y by itself equals, and then ask yourself the question, is there only one expression involving x that can be equal to y, right? So how many expressions involving x are over here? If the answer is just one, it's a function. Y is a function of x. If it's more than one, then y is not a function of x. You'll see what I mean, hopefully, when I go through some of these examples. And I'll also show you some graphs too, and I'm going to go to a calculator for some graphs, but anyway. All right, so example 6. All right, example 6. 5x plus 2y equals 10. So I solved this for y. All right, so we'd have 2y equals, negative 5x plus 10, right? I would subtract 5x first, and then I would divide everything by 2. So y equals negative 5 halves times x plus 5, right? Now, I'm hoping that you recognize this as a linear equation, right? If you were to graph this thing, and I'll make a rough sketch, and then I'll go to a calculator for a better picture. But this would have if x were 0, y would obviously have to be 5. So the ordered pair 0, 5, 0, 5 is in this picture, is in this relation, right? If x were 2, then output would be 0, right? So input 2, output 0. If x were 2, y would be 0. And those are like the x-intercept and y-intercept of the graph, right? But then there's infinitely many ordered pairs, right, that satisfy this equation, right? And they form a straight line like this. There's a graph of all the infinitely many ordered pairs that belong to the relation described by this equation. Now, I mentioned that vertical line test earlier, right? You draw any vertical line, it's going to hit the graph exactly once. Right? Draw any vertical line, it hits the graph at most once, right? Never more than once, right? So this is a function. Y is a function of x. And notice here, when I solve for y, there's only one expression involving x on the other side. Right? There's only one expression. You take your value of x, you take your input, you multiply it by negative 5 halves, and then you add 5. That's going to give you one value for your output. So every value of x pairs with just one value of y. So this is a function. Y is a function of x, right? Because every value of x pairs with at most one value of y. I hope that's clear. And again, I'll go to a free online graphing calculator. It's at a website called Desmos.com. Right. It's a free graphing calculator, and I'll just enter the equation they gave us. 5x plus 2y equals 10. Right. And again, you're seeing this line, and every x coordinate goes to one y coordinate, right? Not more than one. And that's that vertical line test I mentioned, right? If you draw any vertical line, it's never going to hit the graph more than once, right? So every x, every vertical line kind of corresponds to a certain x value. Right? Okay, so you can see from this that it's y is a function of x. Great. All right, now in example 7, we have, x equals y squared. All right, x equals y squared. Now, you may recall the square root property. When I have a quantity squared equal to another quantity, then, I'm trying to solve for y here. If y squared is equal to x, then y is either, the principal square root of x, or y equals negative square root of x. So you see, when I try solving for y here, when I solve for y, there are two expressions involving x that y can be equal to. Or you might write y equals plus or minus the square root of x. But yeah, that's what I meant over here. If you solve for y, like I have, and there are more than one expressions involving x that y can be equal to, then y is not a function of x. So I can write that right now. Right? Now we'll see it in more detail in a second. Right? Y is not a function of x. All right, let me show you a specific example, why this is the case. How come y is not a function of x? Now, x is a function of y. All right. If you switch those, x is a function of y. There's only one expression. When you solve for x, which it already is, there's only one expression involving y that x can be equal to. All right, so be careful with that. They might ask you some other way around stuff, but y is not a function of x. For example, suppose x were 1. If I replace x with 1, well, then you'd have 1 equals y squared, which would lead me to the fact that y could be equal to 1 or negative 1, right? 1 squared is 1, negative 1 squared is 1. So this relation has these ordered pairs. 1, 1, x is 1, y is 1, and 1, negative 1, right, belong to the relation. Right? They belong to this relation, meaning that y is not a function of x, right? If x's are my inputs, again, x here, when they say it this way, x's are the inputs, y's are the outputs. We have 1 pairs with 1, 1 also pairs with negative 1, right? If I had little arrows, here's 1 on the domain, and then 1 and negative 1 in the range, and we'd have the 2 arrows coming off of it, right? That's not good. That's not a function. Right? Okay. And let's take a look at a graph of this thing. Right, might as well, right? So we had x equals y squared, right? X equals y squared. Look at that. You see, this definitely doesn't pass that vertical line test, right? If I were to draw, say, x equals 5, right? There's a vertical line. And you see this point and this point are on the graph. It hits the graph twice, right? In fact, any vertical line to the right of 0 would hit the graph twice. So that means every x value bigger than 0, pairs with 2 different y values. That's more than 1. That's not exactly 1. Right? X equals, I just said x equals, how about x equals 4, right? 4 pairs with 2 and negative 2. That's not a function. Right? X equals 1, like we just did. See? 1 pairs with 1 and negative 1. Not a function, right? So that this blue graph is not the graph of a function, or y here is not a function of x. Right. Great. Right, I'm doing that again with basically I think the rest of the video. Right. A bunch of examples. All right. So here, again, I'm gonna try first to solve for y and see, do I get just one expression involving x or more than one expression involving x that y could be equal to. All right, so here again I have a y squared, so you can probably guess that just like in example 7, this isn't, y is not going to be a function of x. All right, here we'd have y squared equals 6 minus 2x, or negative 2x plus 6. And then once again I'd apply the square root property and say that y could be equal to the principal square root of 6 minus 2x, or y could be the opposite of that. Negative square root of 6 minus 2x, right? All right, so for example, again, if the input was x equals 1, we'd have y equals, we'd have y squared equals 4, right? 6 minus 2 times 1. And if y squared is 4, that means y could be 2 or negative 2. Right? Going into both of these equations here. Right? There are 2 expressions that y can be equal to that involve x in this equation. And because there are two, there are more than one, they would say that y is not a function of x here. Right? Each value of x doesn't correspond with at most one value of y. You know, there are some values of x that correspond with more than one. Right? You'd have the ordered pair 1, 2, and the ordered pair 1, negative 2. Right? So all this stuff put together says that y is not a function of x. In this particular equation. Now again, if they ask the other way around, is x a function of y? Yes, yes it is, but we're not asked that. All right, so don't worry about that here. Let's go to the graph. All right, I'm gonna put that equation in, and we'll see. All right, we have 2x plus y squared equals 6, and you can very clearly see that this would not pass that vertical line test. Right, again, if I put in a vertical line, x equals 1, right? See how it hits that blue graph at 2 and negative 2. One input 1 pairs with output 2 and negative 2. The input of 1 pairs with more than one output. That's not a function. Right? And again, any vertical line, looks like any vertical line to the left of 3 here is going to hit the graph more than once, right? X equals 0. The y-axis hits it more than once. X equals negative 4, right? Hits it here and here. Right? So each input, each value of x that's less than 3 is pairing with more than one output. Clearly not a function. Y is not a function of x. All right. How about here? Y equals 1 over x. Well, this one's easy enough. Y is solved for, and look, there's only one expression over here that involves x that could possibly be equal to y. So y here is a function of x. Every value of x that's allowed to be plugged in, of course, because you can't divide by 0. Remember, x can't be 0 here. Right? You can't have denominators of 0, but for every other value of x, just like up here, there, x couldn't be, greater than 3 because you can't take square roots of negatives and all that, right? Here, x can't be 0 because you can't divide by 0. Anyway, for any allowable value of x, there's exactly one value of y it pairs to. So y is a function of x here. Fantastic. All right, let me show you the graph of this one. All right. I could do it by hand, but I'll just make a cleaner picture with the Desmos site here. Y equals 1 divided by x. Look at this black graph showing up, and look, no matter what x equals, a, I'll just add a slider for a, not x equals k. What's going on here? Alright, well anyway, x equals 1. That should be vertical lines. Maybe if I put... I don't get why it's doing that. Anyway, x equals 1, hitting the graph there. 1 maps to 1. 1 pairs with 1, and that's it, right? It doesn't hit the graph again up here anywhere. It doesn't hit the graph down here anywhere. And I can just move this anywhere I want, right? X equals 0 doesn't hit it at all, but that's fine, right? As long as no vertical line hits the graph more than once, you have a function. Right? But if any vertical line hits the graph more than once, it's not a function. Y is not a function of x. Here's x equals negative 3. Right? Hits the graph here and nowhere else. Right? And I can keep going with this, and you can see any vertical line is going to hit this graph at most once. So we do have a function. Y is a function of x. Excellent. All right, now once again, you're probably thinking, hey, look at this, there's a y squared. Yeah, you're right. Chances are y is not a function of x here. Okay. If I was trying to solve for y, first thing I would do is get rid of the square root by squaring both sides. And we have x squared equals 1 minus y squared. And then we'd have y squared would be equal to 1 minus x squared, right? Just adding y squared, subtracting x squared. And then just like all the other problems we've seen so far with y squared equals a number, applying the square root property, y is either equal to the principal square root of 1 minus x squared or the opposite, right? The negative square root of 1 minus x squared, which again, you can just write plus or minus. But there are two expressions involving x. There's more than one expression involving x that y can be equal to. So we're seeing from that y is not a function of x. There are values of x that you can plug in that will pair with more than one value of y. So for example, right, if x equals 1 would be a bad one because you'd get 0 for both of those there. So how about x equals 0? Right? If x equals 0, you'd have y equals 1 or y equals negative 1. Right? So you'd have the ordered pair 0, 1 and the ordered pair 0, negative 1 in this relation. 0 pairs with more than one value, more than one output, more than one value of the range. So again, y is not a function of x. And let me put up the graph of this. Right. So back on the Desmos site, here it is, right? X equals the square root of 1 minus y squared. And look at this. I mean, it's a small graph. It's actually the right half of a circle. All right. Maybe you can see that. And look. See, I put in the vertical line x equals 0. Right? Just the y-axis, and you see there's 0, 1. There's 0, negative 1. It hits the graph more than once. X equals 1/2, right there. That hits the graph more than once, right? So basically, any vertical line from x equals 0 up until x equals 1 only hits it one time, but anything from 0 up to 1, not including 1, will hit the graph more than once. So this is not a function. Y is not a function of x here, as we already saw. Right? You don't need a graph to say that. Wonderful. Then example 11. Again, we're seeing a y squared here, so, usually y to an even power will more than likely imply that y is not going to be a function of x. Watch this, right? We try solving for y. Y squared equals 9 minus x squared, and that's very similar to the previous question. So y could either be the principal square root of 9 minus x squared or the negative square root of 9 minus x squared. But either way, there are two expressions involving x. There's more than one expression involving x that y could be equal to. So that leads me right away to saying that y here is not a function of x. Right, and nor would x be a function of y. The same thing would happen with if you solve for x. In number 10, x is a function of y. But here in number 11, x would not be a function of y, so it wouldn't work either way. And you can verify that for yourself if you want. And then just one example to show you, again, very simply, if x were 0, y would be 3 or negative 3, right? There's two of them, right? So 0 would pair with 3. 0 would also pair with negative 3, leading you to the statement, hey, y is not a function of x here. Right. And again, on the Desmos site, I'll punch in the equation they gave us. X squared plus y squared equals 9. Look at this circle. It's a circle centered at the origin with a radius of 3. We'll talk about circles in later videos. And clearly, right, you can put in all sorts of any vertical line from x equals -3 to +3. Any vertical line between those will hit the graph more than once, right? Like x equals 1. There it is. 1 pairs with 2 different outputs. 0 pairs with what we said on paper, right? 0 pairs with 3 and -3. You're seeing it hit the graph twice, right? Okay. So again, y is clearly not a function of x. Right. Great. I'm keeping this going. Right. So example 12, another equation which represents some relation with infinitely many ordered pairs, and once again we are asked, is y a function of x, right? Does every x pair with every allowable x pair with exactly one value of y? Well, here it's y cubed, odd power. There's no so it's just simply y would be equal to the cube root of x, and that's it. No positive or negative here. It's not an even power. Right? Yeah, and that's it. There's only one expression. Only one expression involving x that y is equal to. So that tells me that every value I can plug in for x will give me at most, pair with exactly one or none, but here it's exactly one value of y. So y here is a function of x. Function of x. Wonderful. And again, let's look at the graph, and you'll see that it passes that vertical line test. No vertical line will hit the graph more than once. All right, and here it is. X equals y cubed was the equation they gave us, and look at this, right? Now you can zoom in more and see that this isn't straight up and down. It's actually at an angle. I know it looks straight up and down here, but it's not. It's just very, 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 very sharply rising here. So that might be a bit tricky, but when x is 0, y is 0, and that's it. When x is 1/2, y is the cube root of 1/2, and that's it, right? So every x value corresponds to exactly one y value. Every vertical line is going to hit this graph in one point, and no more than one point. Great, so y is a function of x here. Okay. Example 13, it's already done for us. Y equals, and then just one expression involving x. So just like 12, we have y as a function of x. Y is a function of x here. Fantastic, right? Each allowable value of x will be paired with exactly one value of y. Right. Now, if you were to switch it, and if they asked you, is x a function of y? The answer would be no. All right, you can figure that out for yourself. But y is a function of x. Let's see that in the graph here. Put in y equal. This is actually the top half of a circle. You'll see y equals the square root of 1 minus x squared. And look at that, right? The top half of a nice circle, a semicircle, and any vertical line you draw is going to hit this graph, this green graph here, one time, and no more than one time, right? So again, y is a function of x this time. All right. Next one. look at this. Now you remember what this means. We have y equals plus or minus the square root of 1 minus x. This is two expressions written as one expression. Right? Just, a lot of times to save writing, people put plus or minus. Remember, this means that y can either be the principal positive square root of 1 minus x, or y can be the negative square root of 1 minus x. So again, there's more than one expression involving x that can equal y. So y is not a function of x here, is not a function of x. And again, I can give you a quick example. Now here x has to be, remember you can't take square roots of negatives when you're dealing with real numbers. So x has to be, less than 1, less than or equal to 1 here. Now when x is 1, y is 0, and that's it. So that's not a good example. But when x is, negative 3, y is either going to be 2 or negative 2. All right, plus or minus 2. So negative 3, because it'll be the square root of 4, right? 1 minus negative 3, 1 plus 3. So negative 3 will pair with positive 2, but also negative 3 will pair with negative 2, right? So the same inputs going to two different outputs, more than one output, tells you that y is not a function of x. We do not have a function here. All right, and then once again, going back here, now you have to enter them separately. I can't do the plus or minus thing, I don't think. Plus or minus. Yeah, I don't think you put the plus or minus symbol in. So I have to do one with the positive, right? And then one with the negative. Plus square root of 1 minus x minus square root of 1 minus x. And you're seeing this. Now I should make them the same color because they are part of the same graph. Right? So let's make them both purple. And there's your graph. And definitely, right, definitely does not pass that vertical line test. Right? There are, for any value of x less than 1, you're going to be hitting the graph twice. Right? So y is not a function of x here. Okay. All right, so just a couple more problems. Almost done. All right, so one more of these where again I'm given an equation and I'm asked, is y a function of x? Does every allowable value of x pair with exactly one value of y? Again, it's y to an odd power, so this is simply y equals, the cube root of x squared. And, that's it. Or x to the 2/3 power if you remember your fraction powers, same thing. But still, there's only one expression. There's only one expression involving x that can be equal to y here. So y is a function of x this time. All right. And if you were to look at a graph, it'll pass the vertical line test. All right, let me show you one more time. One more of these here. Y cubed equals x squared, and look at this, right? You could draw any vertical line, right? Any vertical line, and it's only going to hit the graph one time. All right, it's no vertical line will hit the graph more than once. So we do have a function here. Y is a function of x. Excellent. All right. And then, for some reason, I picked this last exercise. We're back to a table with just 3 ordered pairs. All right, 3 ordered pairs, back to just a table. So 5, so again, usually x will represent the inputs from, the values from the domain, and the y's will represent the outputs, right, the values from the range. So like the domain here is the set of, 5, just 5, 10, and 15. The range here, and I guess I should have mentioned in all those other problems, domain and range can be infinite, right, have infinitely many values in it. for the last example, the domain was all real numbers. Example 15, you could plug in any value for x on the real number line. And the range was all values 0 and greater, from 0 to infinity, right? So just understand that the domain and range can have infinitely many values as well. And the range values, the value, just 3 and 8. Again, no need to write repeats. Right? Just state what outputs show up. And then this is one where I could do the arrow diagram thing again. 5 corresponds to 3, 10 paired with 8, 15 also paired with 8. But you see how every value of the domain has just one arrow coming off of it. This doesn't matter, right? A lot of people look at the 8 and say, hey, there's 2 arrows coming in. So this isn't a function. No, 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 no. Remember, the definition of a function only has to do with the domain values. And, each value of the domain is going to exactly one value of the range, right? Every value of the domain has one arrow coming off of it. So this relation is a function. Y is a function of x here. So y is a function of x in this particular chart. Now, if for some reason they changed it around and said, is x a function of y? Right? Then the answer would be no. I'll write that much at least. Y is a function of x. However, x is not, and I've said this out loud for other problems, but I left it to you to look at. X is not a function of y. Right? Because you have y value of 8 that corresponds to 2 different x values, right? 10 and 15. Right? If you were doing it the other way around, you'd have y. If you have y values corresponding to x values like this, there'd be a y value, an input that corresponds to 2 different outputs, right? Again, if you change the definition, if you call the y values the inputs and the x values the outputs. So please understand that switching the quantities can make a difference. So y here is a function of x, but x is not a function of y. But that's not what we were asked. We were just asked about y. Is y a function of x, right? So you can kind of ignore what I wrote down here if you want. Okay, wonderful. All right, and that's it. All right, well, pretty long one there, a little over an hour, almost an hour 12, hour 13. But I'm hoping that watching me go through the definitions and going through these 16 examples, hopefully these help you in some way when you're asked to determine whether a given relation is a function or not, right? If one quantity is a function of another quantity. And thank you very much for watching.